Thanks very much. So I'm going to be talking about static analysis of hundreds of Python extension modules, and with a rather ghoulish title of Death by 1,000 Leaks. So what do I mean by static analysis? I mean to discover properties of a program without having to actually run that program. So having a program that accepts other programs, treating them as data rather than as code, so that we can walk over that data and find bugs in them. And the kind of code that we're going to be looking at, or data if you will, is the C code that makes up Python extension modules. So obviously, hopefully you have some familiarity with Python. This is PyCon. Hopefully it's at least some familiarity with C, maybe C++. Maybe you've written and hand-coded C extension modules for Python and you really, really know that. Maybe you've taken the smart option and auto-generated your extension module using some method that may have been addressed in a recent talk that I didn't catch, so I don't know about that. Maybe you were stuck with one of these things and you found yourself stepping through it in the debugger, maybe not really understanding the API, but trying to track down a problem. And maybe that's enough knowledge to understand this talk. So I'm going to be talking about cpychecker, which is the analysis tool that I wrote, and what it does and how you would go about running it on your own code. And then talking about my experiences running it on hundreds and hundreds of extension modules, and basically what I discovered doing that. So cpychecker, it lives as part of my GCC Python plugin source tree, and there's a link on the screen in order to check that out from Git, and the docs URL as well. It's part of the Python plugin for GCC that I wrote. So GCC is the GNU compiler collection. It's a suite of compilers for many different programming languages, and it supports a plugin interface so that as your C code is being compiled, you can have a plugin that analyzes the compiler's representation of that code and potentially injects new compile time warnings. And so my Python plugin embeds the CPython interpreter as a GCC plugin so that you can do that writing Python scripts that run as your C code is being compiled, injecting new compile time warnings or visualizations or whatever. So cpychecker lives as the kind of major example within the Python plugin source tree. It's 6,500 lines of Python code that basically implement lots of verifications for different problems that typically occur in C Python extension modules. I gave a talk on this at PyCon last year and went into a big deep dive into how it works. This talk will be a bit more high level than, well, I gave you the summary a few slides ago. So the main reason I wrote this tool is because I got sick of tracking down reference counting bugs by hand. Every object inside the CPython interpreter has a number of pointers pointing to it, this block of memory, and it has its own view at the top. If an object can have a view, it's just a blob of memory, anthropomorphization, whatever. The obrefcount field, which is the object's view of, well, how many pointers do I think are pointing at me? And your responsibility as an extension module author is to use incref and decref to ensure that that accurately reflects the reality of the memory of the process. And so there are two ways of getting a number wrong. You can have the obrefcount field can be too high or too low. If it's too high, you have, say, an object that nothing is referring to, but its obrefcount field is, say, 1. And it says, oh, there's a pointer left in memory that is pointing to me. I'll stick around until it goes away, and it'll never go away, and you have a memory leak. And if you have that pattern occurring in a loop, the memory usage of your process will go up and up and up and up. And of course, if anything, that object is in turn referring to other objects, they too will have leaked. And indeed, if any of those objects are small and are being allocated out of CPython's optimized allocator, the whole of the 256K arena that object was allocated from can never be reclaimed to the system. The opposite problem is if the obrefcount field is too low. So you have a blob of memory that the obrefcount field hits 0 and it gets cleaned up because there aren't any pointers pointing to this anymore. But if in reality there are pointers pointing to this block of memory, that memory gets reused for something else, and then at some later point the pointers get followed to access the object that ought to be there, and boom, and bad things happen. You may well segfault the interpreter. So the cpychecker, basically, for every source file that includes python.h, it tries to analyze every function and every possible path through those functions and every possible object that can exist in every path, with some limitations that I'll get to, and figures out, well, how many pointers are actually pointing at these objects, and what is the activity of the obrefcount field of those objects and basically warns you when these two values get out of sync with each other. And it'll generate an HTML report. So I hope this is relatively visible. We have a simple method here that allocates a list at line 27, a PyList object of length 1. And line 30, it makes a PyLong object with PyLong from long. And at line 36, which isn't highlighted but is at the bottom, it basically sets item 0 of the list to be the item using PyList set item. And what this HTML report is showing is that at line 27, as control flow goes through the function, it considers the case where the PyList new call succeeded. You have a new PyList object, and its obref count is 1 plus n, and that basically means that you own a reference, and there may be other references that we don't know about. The checker basically treats that in an abstract way to track the maybe this is too much technical detail for this particular talk, but eliminating the case that an object could have been deallocated because there may be references we're not tracking. But anyway, it's considering the case where the PyList new call succeeds. So we have a non-null pointer to a list object. So the error handling case at line 28, we don't handle that. We instead go through to line 30, and we go to the PyLong from long call. And now it's considering the case where the PyLong from long call can fail. Potentially we're low on memory. And we go on to line 33, we got a null item back, and we go into the error handling path into line 34 and return null. And at the bottom it's saying, well, we have a problem here. The ref count of, the ob ref count of list is 1 too high. Because nothing at the end of this function, it's gone out of scope, there aren't any pointers left in memory referring to this list item. It ought to have an ob ref count field of 0, or at least 0 that we know about. There's that n for anything else and the whole of the rest of the program that we're not simulating. So the ref count field ought to be 0, but it's detected looked at the activity of the ob ref count field and seen that actually the ob ref count field is 1 plus that abstract n. And so we have a memory leak. And so this method leaks memory when it follows this particular flow of execution through the function. And so it will emit you reports describing the memory leaks and so on in your code. Unfortunately, it's not perfect. It only operates at one function at a time, rather than considering the interaction of all the functions in your code, meaning it's an intra-procedural checker rather than an inter-procedural checker. And so it has to make some assumptions about the reference counting behavior of all the functions that, well, it's only considering one at a time. So it assumes that any function that returns a PyObject star is returning you a new reference rather than a borrowed reference. Now, it does actually support some compiler attributes so that you can mark your functions that return borrowed references, but it would be better if it just figured that out for itself. Patch is welcome. Where was I going with that? So if you have pre-existing code that uses lots of borrowed references, it'll unfortunately give you lots of false alarms. Sorry. It does know about most of CPython's API. I've given it lots of basically hard-coded rules explaining in particular the functions that return borrowed references and that steal references. That's another thing that can cause false alarms. But it knows about the ones in CPython that steal references. The way it handles loops is I optimized for precision of analysis of liveness of objects and pointers, which basically means I only ever analyze for a loop, not going into the loop and going 1 times through a loop. And then I basically give up to ensure that the analysis always terminates. So this obviously mathematically is incomplete and is maybe something of a hack, but it means that it ensures the precision of the analysis, and it's I think basically a choice to ensure that we get the kind of memory leak checking that's kind of my focus of the tool. Unfortunately, the internal representation can sometimes explode on code that you might think is relatively simple, and it starts using a lot of CPU and a lot of memory. And there are some tunables to tweak that. But yeah, again, there's some improvement is possible there. As well as checking for reference count problems, as it's trying to analyze these different paths through your code with the caveats I just gave, it also looks for lack of error checking. So if you have for example, if you remember the example a few slides ago where we had a call to pylist new, when our pylist new typically gives you a new list object back or a new reference to a list object, but it can also fail. For example, if you pass in a negative size or if memory is low, you'll get a null pointer back and an exception will have been set. And if you have C code that blithely uses the result of pylist new, assuming that the result is non-null, i.e. it dereferences that pointer somehow, you will crash. When that call returns null, you will get a crash of the interpreter. Well, the behavior is undefined, but typically you'll have a segmentation fault of the interpreter. And so it will warn you about, basically it'll consider the case where pylist new fails, and considering that be to null, and give you a warning that, you'll have a crash here because of a null. Similarly, many of the CPython API calls, if you pass them, require you to pass in a non-null value, and will, again, crash the interpreter, typically, if you pass in a null value. And so it will, again, cpychecker will warn you when you mess that up, or if you fail to have error checking. Plus, there is some additional checking it does on every path through the code, which I give on this slide. And it also does some, as well as the checking all the paths through the code, again with the caveats, it does some similar, what I call type checking. And the classic one here is pyarg parse tuple and its friends and pybuild value, which are, you'll know as calls in the Python API for marshalling data between the Python world and the C world, and then back again for pybuild value. And they take a string which is a series of control codes and and then a C level arguments. And those control codes, it's a little mini language that has to exactly match the C-level types that follow. And a plain old C compiler has no way of checking that you got that right. And unfortunately, if you get it wrong, you can crash the interpreter, have data corruption, and memory leaks, or no problem at all, and you can have problems lurking. So cpychecker warns you, understands that those little mini languages, and warns you about them. And there are a few other similar checks that it adds, which I give on the slide as well. There are a few things that it doesn't check for, and there's some ideas I had in terms of what it could check for, and it doesn't yet. I'm going to be around for a couple of days for the sprints after PyCon, if anyone's interested in hacking on this and adding new checking. And also, if you have ideas for things that it could check for that I haven't thought of, that would be great. And of course, it's not telepathic, it can't read your mind, and in particular, you probably don't have a specification for your code, or at least not one that's machine readable. And so it can't check that your code is actually doing what you thought you intended it to do, unfortunately. So in terms of how would you go, that's what it is, how would you go about running it on your own code? So I'm hacking on it regularly. I'd recommend grabbing the code from Git and getting involved on the mailing list. That's the way to do these things. So there's the how to check it out from Git. It has various dependencies. Because it's a GCC plugin, you need the environment for building a GCC plugin. It'll run on GCC 4.6 and 4.7, and I've almost got it working with 4.8, which is good, because the first pre-release candidate of 4.8 was released today for GCC. And so here are the dependencies on Fedora, which is the operating system I use. Obviously, this will need adjusting for your OS, and I can help with that if anyone runs into issues. So I normally do make plugin, builds the plugin, and I had to go writing the world's worst Python extension module to write some C code that uses the CPython API, compiles cleanly on a regular C compiler, and if you do make demo, then it'll use the freshly built cpychecker to run it, and it will emit this wall of errors. So it's line demo.c, line 90, we have a 32-bit versus 64-bit type mismatch in a pyarg parse tuple call. Line 1 or 2, we have a memory leak, and so on and so forth. But it gets a bit much to read after a while. So again, there's the HTML view, which I mentioned earlier. So assuming you've built the plugin, and how would you go about running it on your own code? If you're using dist-utils, so you normally set up.py build, you basically, there's a helper script, GCC with cpychecker, that you need to ensure that gets run rather than the regular GCC. And so just set CC in your environment to point to it as given in the top half of the slide. And if you're old school and use makefiles, then set a makefile variable using the syntax at the bottom. So please, yes, do try it on your own code, and the mailing list information is given on the screen, and I'm very interested in hearing how you get on. Hopefully, well, I say hopefully you'll find bugs in your code. Do I mean that? I'm not sure. Hopefully if there are bugs in your code, you will find them, but you may well run into bugs in cpychecker itself. So we can discuss those on the mailing list. So I set myself the goal of analyzing all of the Python extension code in a major Linux distribution. So I work on Fedora, so Fedora 17, which is a relatively recent release, thanks, and looking at everything that linked against libpython 2.7, which is lots of small packages, and also you have these big packages where there's a little subdirectory where it contains the Python bindings, which so about 370 packages. And try to just analyze everything and see what I came up with. And so the way I did this, because I'm using an RPM-based distribution, the whole issue of is this disutils, is this makefile, is it cmake or whatever, is kind of solved already by, it's encoded in the source package. We have a tool in the RPM world called mock, which is not a tool to do with the mock object tool. It's a virtual builder tool. So it provisions effectively a virtual environment with exactly the dependencies you need to build a tool. You then get the source code, it builds, you extract the artifacts of the build, and then tear down the virtual environment. And so I thought, well, I can reuse this to inject static analysis. So I came up with mock with analysis, which has an amusing double meaning. And what this does is it hacks up the GCC within this one-time build environment to inject, so it does the regular build, but kind of off at the side, it's injecting all these static analysis and emitting all that in as a kind of a side channel. And so I'm running cpychecker and various other analysis tools. And the first time I did this, well, I did all of this. I did a big pass. I generated lots of little HTML files, filed lots of bug reports, some of which have been fixed. And then I ran into the issue, which is, yeah, great, I've got lots of little HTML files. What do I do now? So for the second time I did it, I came up with this data model, which I call Firehose, which represents in a kind of common format for representing all the different warnings from all these different static analysis tools, describing warnings found in source, issues found in source code, potentially with a trace of execution through source code in order to reach the particular issue, and with various kinds of metadata. That's an XML format, so Firehose. And that, I also put in some bulletproofing so that every analyzer just gets a minute to do its thing, and if it hasn't reported back, we just kill it, so that let the build proceed to try and ensure that if an analyzer goes off into the woods, which cpychecker sometimes does, we at least get some level of coverage on everything. Capture everything in this common data model. I'm currently just putting it into MongoDB. And also any sources that get mentioned, I can squirrel away as well. And I found that doing this, I could actually made it really easy to capture code metrics. So I did the popularity contest of, within the CPython API, what are the most commonly used entry points? And it turns out in this data set, pyarg parse tuple is the winner with just over 3,000 call sites, closely followed by pyr set string with just under 3,000. And then there's a big drop off to pybuild value, but the and keywords variant is much less used than the regular parse tuple, and the size t variant, if you know that, is kind of a distant second. And in terms of the long tail, there are lots of entry points in the CPython API that just get used once in this whole corpus of data. And in fact, when I looked at these, it turned out that 2/3 of the entry points were people violating PEP 7 and using py something for their function name. And the other thing I found is actually really easy to do across this whole body of code. What's the cyclomatic complexity of, which is it's a classic measure of that some software QA people use to measure how complicated are the insides of a particular function. And this is a kind of an unfair slide, because the top one turned out to have a complexity of 1600, which is wildly, scarily huge. But this is actually running on, this is a really unfair slide. I apologize to the projects that are on it, because this is after it's gone through the C preprocessor. So all your PyIncrefs and all your PyDecrefs have already got a control flow branch for them. And also, many of these things are auto-generated C code. So frankly, if you're working from a high-level representation, that's what you should be looking at. But yeah, so this approach gets us to do quite a lot of nice code analysis things. So in terms of the complaints, and this slide attempts to show the tool and then the test within the tool and the frequency within, I hope that's readable, within which the thing, and unfortunately I haven't yet been able to break out the LLVM's Clang analyzer into separate things. But yeah, after that, the topmost is a mismatching type in format string from cpychecker, and then reference count too high, and there's some GCC warnings, which, well, I'll skip onwards to. So looking at cpychecker warnings within this data set, the topmost is almost 3,000 warnings about mismatching types in format strings. And when I looked at this data, I found that actually these are mostly false positives from my tool. And so, but there are a lot of real bugs hidden in the false positives. So this is a valuable test, but I guess what this data is telling me is that we need to improve add some heuristics to make the test a bit better. The next one is a reference count too high, which is if you're assuming it understands the new versus borrowed references, that's generally a true positive. Returns null without setting exception, it's the third one on the list. That, unfortunately, is generally a false positive from the tool because it doesn't have the interprocedural knowledge to know that something else set an exception on this thread local state, and so on. And if we'll dig down, one thing about this slide that I like is that right at the bottom of the long tail, where there's this big drop-off there, for example, missing null terminator in PyMethodDef table. That's almost, I believe that's always a true alarm. It's never a false positive. And that is a time bomb in your code waiting to kill you unexpectedly, because that basically you're relying on whatever value after this thing in memory happened to be 0. Otherwise, when your module starts up, it'll just go on forever, and you'll probably get a segmentation fault at some point, because you're relying just on random artifacts of the data layout from the linker. So there's some real kind of, are they gems hidden in the data? Well, whatever the opposite of that is. Reference counting warnings, I found that people tend to get reference counting too high rather than too low, with a ratio, was that 5 to 1. And I guess what my hypothesis is what people are doing is they're coding things up until it kind of works. And because a reference count too high basically just gives you a leak that you may not notice, whereas a reference count too low kills you, or kills the interpreter. And one of the classic ones here, I found about 7% of the reference count too low were this classic one where you're trying to return none from a method. Now, if you're returning an object from a method, you're meant to be returning a new reference to an object. So if you blithely return the PyNone singleton, or naively, you're forgetting to do an incref on it. And if you call that method enough times, the interpreter will bomb out with the error message given at the bottom. The way to fix that is a pre-canned macro to fix that, which is PyReturnNone, which does the incref for you. One pattern I saw happening quite a few times, this is kind of the stuff I wasn't expecting to see. PyBuildValue. PyBuildValue lets you assemble either an object or a tuple if you have multiple arguments. So this code here at the top is attempting to construct a pair of objects, a two-tuple, from some object we've constructed higher up in the function, and then a C integer value. And that's if we own that reference on that, or the O control code to PyBuildValue adds a new reference into the newly constructed object, and we still own that reference on that local. And so that's going to leak. We're missing a PyDecref. And thankfully, there's this pre-canned N control code, which steals the reference into the newly constructed object so that you're no longer responsible for doing that. But one pattern I saw people do was PyBuildValue and just O with a single value and then some object. And what with a single value that's doing is just simply passing the object on, increfing it, and you're doing a memory leak at that point. And if you want to just return an object, just return the object. Don't bother going through PyBuildValue. I think people were just copying and pasting code and not really understanding what was going on. Lots of places missing error checking. And basically, it's so hard to do error checking correctly. So I'm a big fan of the much maligned go-to statement in C. And Yeah, thank you. So the way I like to structure my methods in C extension code is just to have one big error handling block at the bottom and have everything initialized to null at the top. Don't always just initialize everything to null and just have a pyxdecref on anything that own a new reference at the bottom, and have do error checking on everything, doing a goto error at the bottom. And I claim that this is a well-structured programming, but it may not actually be structured from a technical sense. But hey, I think it makes more reliable code. One interesting thing I saw was this, where someone attempted to call a callable using pyObject and then wanted to throw away the result using pyxdecref. And unfortunately, this is horribly broken. This looks plausible at first sight, but because pyxdecref is a macro, and because it actually expands its argument 4 times, the compiler, yeah, so the compiler sees this like that and actually calls the callable up to 4 times, and I actually went through and figured out exactly all the ways in which this was broken, and I counted 10 different bugs in this. So this is in the bug checker, and I mean, ideally we would fix this by fixing the pyxdecref macro, but that kind of scares me because it's it appears everywhere, and what are the performance implications of doing that? So if you're going to do that, put it in a temporary and go through that way. So I've been, so kind of to summarize, I've been talking about cpychecker, which is my static analysis tool for this, and I've told you how you would go about running it on your own code, and then kind of basically what I saw when of this huge data set that I built of running it on basically everything in a Linux distribution. And I guess the subtext of my talk is, do you really need to write your code in C? Because it's so easy to get things wrong. And can you get away with using pure Python code? I'm a big fan of Cython. I didn't catch the Cython versus Swig talk. I'm very interested in watching that. C types, well, it's good, but it has a whole bunch of type safety issues. And there's the new kid on the block, CFFI, which is come out of the PyPy project, and therefore it's probably awesome. But I haven't yet played with it enough to know that have an opinion on it. But yeah, if you do have C code that you feel you must write C code, or you've inherited C code that uses this stuff, please run cpychecker on it. So thanks for listening. All right. Okay. I don't know, do we have time for questions? Hey.
Hi. So thank you for sharing the data on the errors and types of errors and stuff that you found. That's really cool. I'm wondering, of the things you found, how much was found in, say, generated C extension code by Swig or Cython, and issues you filed upstream with their type maps or their implementations or stuff?
Right. So the question was to what extent the data in auto-generated code, to what extent there were bugs there, and what extent there were bugs in the generators. And the first time I did this, I found I got lots and lots of warnings from the tool for code generated from both Swig and Cython, say. And I went through and made it basically clean on Cython, because basically everything I found Cython emitting was a false positive and a bug in my checker tool. And I basically made it cleaner and cleaner. It's not quite clean yet. Swig, I haven't done that for yet. So hopefully that answers your question.
Okay, cool.
Do you know if cpychecker will compile on a Mac or Windows box, or anything that would prevent it from happening?
Yeah, so the question is, will cpychecker compile on a Windows or a Mac box? I have successfully run it on a Mac box, but we had to patch it somewhat, and that patch isn't yet in the source tree. I don't have a Mac box, but yeah, if we can try and actually merge that support, maybe the sprints, that would be good.
Have you thought about, I guess, giving support for Clang and LLVM as sort of like the intermediate instead of GCC?
I have thought about that, and I guess the issue there is, what are the differences between Clang versus GCC? And for myself, sorry, I didn't repeat the question. Clang versus GCC, can we have an intermediate format? I build everything using GCC. That's my everyday compiler, and so it's very useful to me to be able to put everything through GCC, using basically as much as in common as my regular tool chain to add the static analysis, whereas LLVM is kind of the new kid on the block in that regard, and it's not my everyday compiler. So, but I suspect that there would be enough nasty changes to cause quite a bit of work to support both.
I did see the Clang analyzer up there, and I guess it's good to just use as many different analyzers as you can.
Totally, yeah. As many analyzers as possible, throw them all at the problem. Hence it's called Firehose, the XML format, yeah.
So, great talk. Thank you very much for sharing this. I have 2 questions, and the first one is, have you looked at doing this with Clang? So I just wanted to let you know that more than one person had that question.
Right.
But the second one is, with the advent of new stuff like CFFI and C-types, or more code being moved to C-types, and with new stuff like CFFI and Python, you can still get tons of seg faults. Have you looked at other ways to analyze that type of bound C code that doesn't necessarily deal with the Python C API? Or is that something better left to other tools?
So the question is, as things moved increasingly to, I guess, the higher level representations, such as Python or CFFI or C-types, are there ways of auto-detecting bugs using that level? And I guess the answer is, and also there was a reiteration before that of LLVM, sorry to be complete. But yeah, for the second part of that, I guess. Basically, I'm focusing, this tool analyzes the representation of C code as it's passing through the compiler. I guess you would need another checker to analyze the higher level representations, if that's the context of your question.
Yeah, well, I was specifically wondering if this maybe had any techniques that would be useful for such a tool, either for someone implementing it to look at, or if it's a completely different problem.
I imagine there would be quite a lot of commonality between the two, but a lot of the code in the checker is basically modeling how pointers work in C and stack, the heap, and so on and so forth, which might be too low level for those other representations.
Okay, thank you very much.
Thanks.
So the slide where you had the example output of the tool was showing the trace where the object was coming out of pylist new. And it was referring to, it was saying that there was n+1 references left, and there should have been n+0. So I gather its general thinking is that reference counting should be neutral through, by the time you leave the thing, everything should be at 0 where it was before, unless it's returning something.
Yes.
My point is that pylist new is creating a new object, so there are not n unknown references to the object living around. Objects can come into this function from something like pylist new, where it's creating a new object, versus pydict get item or something, where it's going to be an unknown number of external references to it. Would understanding the difference, it looks like it's clear that your tool doesn't understand the difference between those two. Would that make anything better about the analysis, or would it just would making it understand that pylist new returns a new object just make the error message a little clearer?
Both, I guess. So the question was to do with this magic n at the end of pylist new. This is quite a long thing to reiterate.
You don't have to reiterate.
Okay,
yeah,
thanks. And yes, so currently, yeah, I'm merely establishing a lower bound on how many things could possibly. So yeah, a freshly constructed list object, we know at that point there's nothing referring to it. But as soon as we access, well, we could know, and the checker isn't smart enough yet in terms of the modeling in terms of it, but that could be added in terms to establish a upper bound saying actually n is exactly 0, and yes, we could suppress it because yeah, those n's are kind of a bit of a wart in the data reporting, and yeah. There is actually an alternate reporting interface that one of the gentlemen in the third row, I believe you're there, helped work on last year, and that is unfortunately not fully integrated yet, but which shows things in a very different way. So yeah, but yeah, I have a much cleaner separation now internally between model and presentation. Yeah, so now I'm rambling. So hopefully that answered your question.
All right.
Thanks for that talk. I want to return to the Python question that an earlier person asked about bugs in the detecting, ref counting bugs in Python-generated code. I'm maybe 75% confident that there's a bug in the code generated for garbage collecting Python-defined extension types which support weak references. And I wonder if that's something that you noticed at all during the development of this, or if that's something that's too sophisticated or too subtle for the tool to detect, or if it's something that bears further investigation.
All right. So the question describes an extremely complicated potential bug in Python-generated code, and that sounds like an excellent thing to try in an open space. Yeah. Cool. Or we can have a look at the code and see what it emits. That it may well not be smart enough, or it may generate this huge, complicated HTML file. Is actually what I suspect it will do. And yeah, that will make a good use case for version n+1 of the tool.
Great. Well, we should talk about it at some point then.
Cool.
Thank you.
Great talk, David, but I actually don't have a question. I want to answer some for about cleaning the static analyzer. I spent about a week at the end of last year trying to get the clean static analyzer to do just your reference counting. Now, this is prefaced with I don't know Clang internally at all. It's just my day-to-day compiler, and I kind of got somewhere, but it's going to require someone who knows how Clang works, knows C++, and is willing to spend time in the static analyzer, whose documentation is woefully small, but it should be doable, but it would take some work.
Okay, thanks. Okay, I guess it's lunchtime. Thanks. Python interpreter has a number of pointers pointing to it, this block of memory, and it has its own view at the top. If an object can have a view, it's just a blob of memory, anthropomorphization, whatever. The obrefcount field, which is the object's view of, well, how many pointers do I think are pointing at me? And your responsibility as an extension module author is to use incref and decref to ensure that that accurately reflects the reality of the memory of the process. And so there are two ways of getting a number wrong. You can have the ref count field can be too high or too low. If it's too high, you have, say, an object that nothing is referring to, but its ref count field is, say, 1. And it says, oh, there's a pointer left in memory that is pointing to me. Maybe you've written and hand-coded C extension modules for Python, and you really, really know that. Maybe you've taken the smart option and auto-generated your extension module using some method that may have been addressed in a recent talk that I didn't catch, so I don't know about that. Maybe you were stuck with one of these things and you found yourself stepping through it in the debugger, maybe not really understanding the API, but trying to track down a problem. And maybe that's enough knowledge to understand this talk. So I'm going to be talking about cpychecker, which is the analysis tool that I wrote, and what it does and how you would go about running it on your own code. And then talking about my experiences running it on hundreds and hundreds of the plugin, so that you can do that writing Python scripts that run as your C code is being compiled, injecting new compile time warnings or visualizations or whatever. So cpychecker lives as the kind of major example within the Python plugin source tree. It's 6,500 lines of Python code that basically implement lots of verifications for different problems that typically occur in C Python extension modules. I gave a talk on this at PyCon last year and went into a big deep dive into how it works. This talk will be a bit more high level than, well, I gave you the summary a few slides ago. So the main reason I wrote this tool is because I got sick of tracking down reference counting bugs by hand. Every object inside the C extension modules, and basically what I discovered doing that. So cpychecker, it lives as part of my GCC Python plugin source tree, and there's a link on the screen in order to check that out from Git, and the docs URL as well. It's part of the Python plugin for GCC that I wrote. So GCC is the GNU compiler collection. It's a suite of compilers for many different programming languages, and it supports a plugin interface so that as your C code is being compiled, you can have a plugin that analyzes the compiler's representation of that code and potentially injects new compile time warnings. And so my Python plugin embeds the CPython interpreter as a GCC. Thanks very much. So I'm going to be talking about static analysis of hundreds of Python extension modules, and with a rather ghoulish title of Death by 1,000 Leaks. So what do I mean by static analysis? I mean to discover properties of a program without having to actually run that program. So having a program that accepts other programs, treating them as data rather than as code, so that we can walk over that data and find bugs in them. And the kind of code that we're going to be looking at, or data if you will, is the C code that makes up Python extension modules. So obviously, hopefully you have some familiarity with Python. This is PyCon. And hopefully it's at least some familiarity with C, maybe C++. Maybe